In this video, we're going to take a look at acids and bases. We'll first review their properties, and then we'll briefly go over some concepts that you should review yourself independently, such as naming acids, naming bases, and also writing the formulas for acids and bases. We'll then explore acids and bases in a bit more depth by studying pH and indicators, and we're going to see calculations related to stoichiometry and acids and bases as well. Another concept that we're going to explore is the idea of weak and strong acids and bases, and then we're also going to take a look at some different theories of acids and bases that exist. So far you've only really focused on one particular theory of acids and bases, the Arrhenius one, but we're going to introduce you to the Bronsted-Lowry theory of acids and bases as well. So you should review the properties of acids and bases, how they're similar, how they're different. Remember that the properties of acids are due to the hydrogen ions that they create in solution. So let's say H plus for now, and you'll see why I say for now in a bit. And then the properties of bases is due to their OH minus ions that they create in solution, their hydroxide ions. So you can see that the acids and bases differ with respect to several parameters. You should be able to explain the differences, similarities, and maybe even create a Venn diagram to compare acids and bases. You should know examples of common acids and bases. Some should be quite intuitive, or some you may have heard many times, so you should know by now. Do review some of the common bases like baking soda, ammonia, not ammonium, ammonia NH3, one of the common ingredients in Windex, for example. Take a look at some of the acidic substances. So for example, in lemons there's some acid like ascorbic acid or citric acid. So there's many different types of acids and bases that you should become familiar with, just to know some common examples. So 1,000 years ago, when we defined acids and bases, it was based on their taste. Acids were sour, bases were bitter. And today we probably wouldn't do that in the lab. We wouldn't be tasting a substance to determine if it was an acid or a base. We have other tools available to us. We have things like indicators and other properties that we saw in the previous slides that can allow us to know if something has acidic properties or basic properties. So you should review how to name acids and bases. Review the rules for the binary acids and the rules for the oxyacids. If you don't remember them, you can go back to your notes from the previous units, or you can use the notes that I've created for you on the following slides, along with some practice problems and examples. So now we're going to talk about the different theories of acids and bases. We'll start off with the Arrhenius theory of acids and bases. So this here is Arrhenius, and he came up with the idea that an acid is a substance that will create hydrogen ions in solution, whereas a base is a substance that creates hydroxide ions in solutions. So we're going to go and take a look at that in more depth. I'll give you a more formal definition and go over some keywords that you should become familiar with respect to the Arrhenius theory of acids and bases. This is really what you were taught in grade 10 about acids and bases. We tell you OH, base, and then H usually is an acid. So we say, according to Arrhenius, that an acid is a substance that ionizes in water to produce hydrogen ions. And the word ionize basically means that it forms ions. Remember that to form ion, or to have ions in a solution, you should be an ionic compound. Now many acids, for example, HCl, you'll notice is a molecular compound. There's no ions there, so I'm going to write hydrogen chloride gas. Now when I put it in water to dissolve it, HClAq, ions form. So the acids ionize, meaning ions form where there were none before. Plus Cl minus. You'll notice when we get to the definition of bases, bases dissociate, meaning the ions were already there, they just split apart. But for acids, we say they ionize. Some books use the term interchangeably, some professors or teachers use it interchangeably, but I just want to let you know that there is a slight difference between them, but go based on whatever your teacher or professor tells you. So you should be able to write down an ionization equation for an acid. So for example, over here we have HCl. I already did the example over here for you. It's aqueous, it's the acid, it ionizes to form H plus and Cl minus. Whereas if you have the example of H2SO4, so I'm going to take off one hydrogen at a time, you would have H plus, AQ, plus H SO4 minus AQ. So the reason I put minus, not two minus, is because there's still an H attached to it, and that H has a plus. Now this H could come off, but there's different rules when it comes to multiple H's, and we'll learn that later on. You'll learn that in grade 12 in more detail. So focus on examples like you see over here for the ionization of acids. This one here might be a little bit trickier, but just know that only one of the H's will come off, and it's this H over here. You may have noticed that whenever you remove an H, the remaining ion that was attached to the H has a negative charge because that H carried a positive charge. So for example, HCl, when you remove that H, let's just say through ionization, you have H plus here and Cl minus here. It's important that the charges balance out, so H plus and minus make 0. H plus and HSO4 minus make 0. So for Arrhenius, a base is a substance that dissociates in water. And we say dissociate instead of ionizes because the base is already an ionic compound. So the ions are already there, they just separate or dissociate. It's not a decomposition, it's just they move farther away from each other as they're being dissolved in the water. And that increases the concentration of hydroxide ions because the base contains hydroxide. So for example, NaOH will become AQ plus OH minus AQ, and the same idea, the charges need to balance out. Now for acids I did one H at a time, but for base you could just associate the entire base. So for example here I have Mg plus 2 AQ plus 2 OH minus AQ. So you can dissociate the entire base and just make sure it's balanced in the end. So there's some more practice problems for you to try over here. Follow the same rules that we did above to model after the example. Make sure the charge is balanced out. For example, plus 2 here is balanced out by the minus 1 over here, but there's 2 minus 1 charges, so that makes minus 2, which is 0. So for acids, we just did one H at a time, and for bases, do the entire hydroxide. Don't ask why for now, just do that, and later on you'll learn the concept behind why. So here's our summary of the Arrhenius theory of acids and bases. So HCl for acids ionize to form H plus in solution, whereas bases dissociate to form hydroxide ions in solution. That being said, to be a base you have to have an OH, to be an acid you have to have an H that will ionize and separate. In the Arrhenius theory of acids and bases, water is always neutral. It's neither acidic nor basic because the H plus and the OH are equal to each other. And then salts like NaCl, MgCl2, anything that doesn't have that OH or that H in it is considered a salt, and it's always considered neutral because it's not contributing to the pH of to the H plus or the OH minus in the solutions. So again, here we have our summary of Arrhenius theories for bases and acids, and then what we're going to do is we're going to go explore the other theory of acids and bases. So based on Arrhenius' theory, substance needs to have an OH to be a base. But I want you to explore this substance here. This is NH3. This is ammonia. Ammonia is actually a base when you put it in a solution, yet there's no OH. And so I want you to notice this carefully. The ammonia has these lone pairs of electrons here, and that attracts the H, one of the H's from the water, and that becomes ammonium, NH4+, and you'll notice this over here, OH minus. So even though ammonia didn't directly have an OH, it still led to an increase in the concentration of hydroxide ions in the solution by removing an H from water. So that's why NH3 is basic. But according to Arrhenius, an NH has to dissociate in water to form OH minus. Here, NH3 did not dissociate. It just took an H away to increase the OH minus in the solution. So scientists realized that there are some substances that have basic properties that don't have OH, and yet according to Arrhenius, those substances would not be basic. So scientists knew at the time that there had to be some revision to the concept that Arrhenius had come up with. So here are the main problems with the theory that Arrhenius had for acids and bases. So the first thing is that H plus doesn't actually exist. It's just a proton. In reality, when H comes off of an acid, it binds to, let's say, water to form hydronium ions, which is H3O+. But we write down H plus as a summary. So even you'll see your teachers will always write down H plus as a shorthand for H3O+, and we'll just say hydrogens, H plus. But in reality, it's actually H3O+. That forms, not H plus. So that was the first problem with the definition that Arrhenius had. There's no such thing as the H plus swimming around freely by itself. It's going to attach to a water molecule, for example, and form H3O plus. The other problem is what we saw in the previous slide, is that some compounds don't have OH minus ions, but they do produce it in water somehow. So even though they don't have a OH minus ions, they somehow produce it in water. And so they should count as bases, but Arrhenius' theory would not allow for that. And then the last one is that Arrhenius' theory just relied too much on water as a solvent. Acid-base reactions can actually happen in other solvents as well. So that led to other scientists coming up with a different theory, which is what we're exploring next. So Bronsted, Lowry, two scientists that came up with this theory independently. So that's why we combined their names. This O with the line in its Norwegian letter. It's when you pronounce it, it's kind of like between an O and an E. So Bronsted, Lowry, but I'm just going to say Bronsted is what most people say. So Bronsted, Lowry, they came up with this theory that an acid is a substance from which a proton can be removed, and a base is a substance that can remove a proton. So basically it receives a proton. So if we look at this equation here, NH3 takes a proton from H2O. So NH3 is a base. It removed the proton from H2O. So NH2 would be a base here. And you'll notice that water had a proton removed from it. It gave a proton away, let's just say. So that means that water in this case is an acid. So in the Bronsted-Lowry theory of acids and bases, anything that gives away or that has a proton removed from it is considered an acid, and anything that receives a proton is considered a base. So we have base and we have acid. The base removes the proton from the acid. It shouldn't say the acid gives it away. The base has some kind of means of taking it away. So for example, here we have the lone pairs of electrons that's able to attract that H from the H2O to take it away. But you'll often hear us say the acid gives protons, the base receives. That's just to simplify what we're trying to say. So basically for Bronsted, an acid does have to contain an H plus, just like Arrhenius acid. So any Arrhenius acid is also a Bronsted acid. So HCl is an Arrhenius acid, but it's also a Bronsted acid. We still use both theories today in our explanations. But bases, it's a little bit different there. For bases, if there's something that can attract an H plus in the molecule, then that thing's considered a base. It doesn't just have to be OH minus. OH minus can attract H pluses, so that's why it's a base, but other things like NH3 can attract H pluses. Usually if there's a charge, if you have a negative ion or lone pairs, they're going to call it LP, lone pairs, they can attract H pluses and therefore make the substance a base. So essentially, for an acid-base reaction to happen according to Bronsted-Lowry, one substance has to provide a proton, so an H plus, and the other substance has to receive that same proton. So basically it involves a transfer of protons, a transfer of H plus. Now I know I told you H plus doesn't exist. It does exist, just doesn't exist freely in solutions like you see in pictures. It attaches to something. So here, for example, you can take a look at this picture. We have HCl and H2O. The HCl is having its H removed and it's going to H2O. And so there was a proton transfer. HCl lost its proton, H2O gained that proton. So HCl is the acid and H2O is the base in this case. Over here, NH3 received an H. I know that because it was NH3, now it's NH4+. When you get an H, you become more positive. So every H adds a positive, and every H you lose makes it more negative by 1. And the water lost an H, so that makes the water the acid. So water is actually an acid in this condition, but a base in this condition. So according to Bronsted-Lowry, whether you're an acid or a base depends on the context or the reaction that you're partaking in. And so there's a few terms we need to go over when it comes to Bronstet's theory of acids and bases. The conjugate acid-base pairs, and that has two terms in there, conjugate base of an acid and conjugate acid of a base. So if we take a look at this example here, we have HCl as the acid. When it does the reaction, it loses its H, and that H goes to H2O. HCl becomes Cl minus. Now this minus can attract H's. So the Cl minus becomes a base. So the HCl was an acid. Once the proton transfer occurs, the resulting part of the HCl becomes a base. So we call that the conjugate base of the acid in the reaction. So these two here are conjugate acid-base pair. Water received an H. It was a base. Now we have H3O plus over here. This H3O plus can lose an H now. It can go backwards and maybe get rid of that H, give it back to Cl perhaps. So now that H3O plus has become an acid, H2O is a base, H3O plus is an acid. So these here are conjugate acid-base pairs. This is the conjugate acid of the base H2O. This here is the conjugate base of the acid HCl. And they always differ by 1 proton. So if you have an acid that's HCl, its conjugate base is Cl minus. They differ by 1 proton. Cl minus doesn't have that proton. H2O is a base. Its conjugate acid would have 1 more proton. So the base has a conjugate acid with 1 more proton, because the base must have gained the proton to become the acid. And the acid must have lost a proton to become a base. So we'll do an example together on the next slide to identify conjugate acid of a base and conjugate base of an acid. So here we have an example of an acid-base reaction. You'll notice we have CH3COO minus plus H2O. So first you have to identify which is your acid and which is your base on the reactant side. So CH3COO minus becomes this one over here. So it gained an H. If it gained an H, that means that this was a base. And if this was a base, that means that this is the conjugate acid of the base, because now this could get rid of the H and give it away to the OH minus. H2O, let's see what happened to it. It became OH minus. It lost an H, so it's the acid in this case, and the OH minus is the conjugate base of that acid. So in reality, this reaction could go back and forth. So you'll usually see a forward arrow, but then sometimes you'll see a backwards arrow. And usually you'll see that with some of the acids that we deal with in the Bronsted-Lowry theory. Some acids will go in both directions during their reactions. And this here is called an equilibrium. So there's a forward reaction, which means going to the right, and then there's also the reverse reaction, which means going to the left. So here the proton transfer occurred, and then the proton transfer occurred this way, and then the proton transfer can maybe reoccur this way this time to go back to the right. And sometimes the forward reaction will happen at a faster rate than the backwards reaction, but it just depends on different situations, which you'll learn about in grade 12. So you should be able to identify acids and bases in these type of scenarios and identify the conjugate acid-base pairs, which differ by 1 proton. We'll do a few sample problems together on the next slide, and then we'll move on to some indicators and pH. So here we just have some more examples of base and acid pairs that you could study and take a look at. And again, whether you're an acid or a base depends on the context now, not just if you have H plus or OH minus. Here we can see some more examples of water, where water is acting as a base in one situation and then acting as an acid in a different situation. And then here we have our summary of the Bronsted-Lowry theory of acids and bases. Acid is an H plus donor, whereas base is an H plus acceptor. So acid and base reactions in this theory involve transfers of H plus ions, or also called protons, So if I were to give you a substance and I asked you to find its conjugate acid, that would mean that this starts off as a base. So for example, this is a base. Its conjugate acid would have to have one more proton, because if this is a base, to become an acid you have to gain a proton so you can give that proton away. So this would be H3O plus. Over here we have F minus, so its conjugate acid would have HF. Here we have SO4 2 minus, we have one H at a time, so we'd have HSO4 minus. Every H you add takes away one minus. Here we have HSO4 minus, this would become H2SO4. And then you take away that minus to make it SO4. And so they differ by one proton. Here we had one proton, here we have two proton. Here we had no proton, here we have one proton. Here we had no proton, here we have one proton. And so you add H's one at a time to figure out the conjugate acid base. If you added both H's to this here to get H2SO4 over here, it would not be the conjugate acid. They have to differ by one proton by definition. And then the answers on this slide if you want to review and practice. And you can do the same thing for bases. So you know that the conjugate base and the acid have to differ by one proton. So if I'm asking for the conjugate base, that means I'm giving you the acid to begin with. And if I want the base, I'd have to remove a proton so that it could now function as a base and therefore look for protons. So here we'd have SO4, and then you'd have 2 minus. Okay. So same idea here, you'd remove the proton to make it Cl minus. Every time you remove one proton, the substance becomes negative by one more. And take off one proton at a time. And then on the following slide, you can see the answers if you're practicing. Here we have a summary table that compares Arrhenius' theory to Bronsted-Lowry's theory of acids and bases, the definition of acid, base, along with an example, so make sure you review it and understand the differences between the two theories. And then we have some practice problems that allow you to go over the concept of acids, bases, and to identify conjugate acid-base pairs. Here you can see examples of the double arrow where the reaction goes backwards and forwards and backwards. And then sometimes you see the single arrow. So sometimes you have an arrow, a one-direction reaction, and sometimes you have that two-direction reaction. And you'll know when that happens as we study more chemistry. So before we go into indicators and pH, I want to talk about the strength of an acid and base. The strength doesn't necessarily refer to the concentration. So I know sometimes in everyday life we say, oh, this is a strong coffee or a strong tea, and that means that there's a high concentration of the solute dissolved in the solution. The strength of acids and bases does not refer to that. In this case, the strength of an acid and base refers to how good of an acid or how good of a base you are. So what that means is acids are supposed to give away H+, or let's say ionize to make H+ in solution, and bases are supposed to dissociate to make OH- in solution. So they're supposed to make OH- in solution. If an acid is really good at doing that, it's a strong acid. If a base is really good at doing its OH- thing, it's a strong base. If it's not so good, then they're weak acids, weak bases. And I'll go over that with a specific example. So we'll start off with strong acids. A strong acid by definition is an acid that ionizes 100% in water to form H+. So for example, if I took HCl minus, or HCl, and I put it in water, all of the HCl molecules that I put in water, because in reality you're never just putting one at a time, all of the HCl would become H plus and Cl minus. So 100% of the HCl would dissociate to form ionize to form H plus and Cl minus. The acids that are strong acids are these ones over here. For now, you need to know them, recognize them. Okay, so these are the strong acids. There are tricks to know and predict if something will be strong or weak, but the easiest way is really just to memorize these strong acids and then realize that anything else that's not one of these is a weak acid. So what is a weak acid? A weak acid is a substance that, an acid that ionizes very slightly in water, so not 100%. So not all of the acid will ionize to form H plus. So if you look at this example over here, we have CH3COOH plus H2O, and you'll notice that there's some H3O plus forming. But not all of this will actually have ionized. A lot of it will remain behind. And so that means it's a weak acid. And then it goes backwards as well. So then the proton can retransfer back to the conjugate base of the acid. So that's usually where you see the equilibrium, the double arrow. So a weak acid does not dissociate 100% in water. So you can see the strong acid graph over here. You have the strong acid, we call it HA. A could be HCl, for example, Cl, or it could be I, or it could be Br, or it could be NO3. And then you'll notice after you put it in water, all of the HA is gone, and now you have all H plus and A minus. So that was 100% ionization. Whereas here you have a weak acid, HB, and you'll notice that after you put it in water, there's still lots of HB left and only small amounts of H plus and B minus. So some of it did ionize, but not all of it. And that's what makes it a weak acid. So that being said, you should be able to predict which would make a better conductor, the strong acid or the weak acid. Think about ions in solution, right? A good conductor, an electrolyte solution, has a lot of ions. Which one would have more ions in solution? A strong acid or a weak acid? So think about that. If you're not too sure, research it, but think based on what we did here. Here we can see our strong acid example, where all the HCl becomes H3O plus and Cl minus. It's 100% dissociation. And here we can see our weak acid example with a double arrow. It's two-sided. And only a small amount of our weak acid here, our acetic acid, ionized to make that H3O plus and CH3COO minus. And it goes back and forth. So it goes this way, and then the transfer happens in the other way, that way as well. So it's a very weak acid. It does not make it's not all converted into H plus and Cl and the CH3COO minus. So weak acid. And again, you can see this with more pictures over here to go over the concept. Here you have no leftover HA. It's all ionized, and here you do have some leftover HB over here, with some small degree of ionization. The concept of strong acids also applies to strong base. So a strong base is a base that dissociates 100% in water to form hydroxide. And there are some rules that you can use to remember what your strong bases are. Usually hydroxides of group 1 metals are strong bases. So anything here, LiOH, NaOH, KOH, CSOH. And then hydroxides of metals in group 2 are also strong, except for beryllium hydroxide. And then also all metal oxides are considered strong bases as well. A weak base, well, that produces relatively few hydroxide ions in solution. So it's not really good at being a base. It doesn't really have anything to do with the concentration. It's just about how good it is at being a base or how good it is at being an acid. So it's the same concept, 100% dissociation versus not 100% dissociation in the solution. And same idea, weak bases, you'll see that double arrow, whereas strong bases, it's really all towards the dissociation. So you see that one single arrow. And here we have an example of a weak base. Ammonia is a weak base, and you'll usually see that double arrow in the reaction. So this is our summary for the strength of acids and bases. Does not refer to the concentration, but how good they are at ionizing/dissociating. And here you can see a comparison of strong acids and strong bases. It's good to know those strong acids, so you can recognize if there'll be a dissociation, 100% ionization or not. And then you have some strong bases over here. Don't spend all your time memorizing all of these. Just get some experience with it. There are the rules that you can memorize and know if they're acids and bases. For example, here I know that strong acids are strong bases. So here I know that this is a group 1 hydroxide, so it's a strong base. Same idea here. Group 1 hydroxide, strong base. Group 2 hydroxide, strong base. And these are just the strong acids that I listed on the previous slide. So now we'll take a look at the pH scale and how we test for acidity. Remember that many times when we do a reaction with acids and bases, there's not much that happens. I mean, there is a lot that's happening on the inside with the H plus and the OH minuses, but there's not much visually that happens. So we often have to use an indicator like phenolphthalein, the one that turns pink in basic conditions, to see something actually happen. So we can use an indicator to tell us the pH of a solution, which is essentially just how acidic something is. And so you saw this in grade 10. If you were below 7 on the pH scale, 0 to 6 point, and you could have even decimals, so 6.9, 6.98, you're acidic. If you were at 7, then you're neutral, and if you're above 7, then you're considered a base. And you could have 7.2, 7.1, so you can have fraction of pH on that pH scale. Okay, and sometimes if you don't have an indicator, you can use this this pH probe, which actually gives you a number for your pH. So it's a bit more precise there, a bit difficult to maintain, but it's kind of interesting when you get to use those as well. So just a quick review of the pH scale before we move on to indicators and some calculations. Remember that acids have a pH of less than 7, and acidic solutions will have more H3O plus ions and OH minus ions. Okay? Basic solutions have a pH above 7, and they will have more hydroxide ions than H3O plus ions. So a basic solution still has hydronium ions in it, or hydrogen ions in it, but it's just that the OH minus ions will outnumber them. And then a neutral solution will have a pH of equal to 7, that's equal to 7, and they still have both ions in them, but they're equal to each other in terms of their concentration. Remember the square brackets, that means concentration of. So pH is the power of hydrogen, and that basically represents how acidic something is. Less than 7, acidic, 7, neutral, more than 7, basic. And that relates to the concentration of the H plus ions in solution. So pH tells you the concentration of H plus ions in solution. Lower that pH, the higher the H plus concentration ions in solution. There is still OH minus, but H plus greatly outnumbers it. And the higher the pH, the lower the H plus ion concentration in solution. Because as you have a higher pH, you get closer to neutral, and then you get closer, and then you get more basic. And again, here you can see more of a picture example of the pH scale, and you can even take a look at some examples of substances that are acidic or basic solutions, and you can try to find some examples yourself using the picture that's provided up there. One important concept I want to emphasize is that this is a logarithmic scale, a log scale. So there's a fancy button on your calculator that we can use to calculate pH. What I want you to get right now is that each difference of 1 unit actually represents a factor of 10 times. So from 0 to 1, it's 10 times. From 1 to 2, it's 10 times. So for example, if you have a substance that's a pH of 2, and a substance that's a pH of 3, the pH of 2 is 10 times more acidic than the pH of 3. Or you could say the pH of 3 is 10 times less acidic than the pH of 2. You could also say the pH of 2 has 10 times more hydrogen ions. The pH of 3 has 10 times less hydrogen ions in terms of its concentration. So to see how many times more or less acidic something is, you simply do 10 to the power of their difference. So if I had something with a pH of, let's say, 0, and something with a pH of 3, well, I have a difference of 1, 2, 3. So that means that the pH of 0 is 10 to the power of 3 times more acidic, 1,000 times more acidic than the pH of 3. Or the pH of 3 is 1,000 times less acidic than the pH of 0. And that's all because it's on a logarithmic scale. So even though it looks like only a difference of 1, it's actually a difference of a factor of 10 every time you go from one unit to the other. So that's important to understand. You should be able to do some practice problems that are related to the concept of acids and bases. So this is a good one. I'll walk you through it, and then there's some more practice problems on the next page along with an answer key provided at a link. So the pH of an aqueous solution changes from 4 to 3. So remember that the pH indicates the acidity. Lower pH means higher acidity. So this one here is more acidic. So it looks like our solution became more acidic because we have a lower pH. Now if it's more acidic, that means that our concentration of H plus went up. So if you look at the multiple choice, we can already delete some of the answers now. The hydrogen ion concentration didn't decrease. So we can delete everything that says decreased. It did increase. And remember, it's all a factor of 10. All a factor of 10. So it didn't increase by a factor of 4 over 3. There's a difference of 1 between them, so it increased by a factor of 10 in this case. Here are some more practice problems that you can attempt, and you can see the links are provided where you can find the answers to see if you are on the right track. So now we're going to talk about indicators. There's many indicators out there. An indicator is just a substance that changes color in different pHs. So you can use the indicator to figure out what pH you're roughly at. I want you to get that, in grade 10 you would have used litmus paper. So for example, if you had blue litmus paper, it turned red when you put it in an acid. If you had red litmus paper, it turned blue when you put it into an acid, in a base. And if you had a neutral solution, it wouldn't change the color of any of those litmus papers. Here we have some different indicators that are used. I want you to understand that the different indicators will change colors at a range of pHs. So for example, methyl violet at about 0 to 1.6, it turns it goes from yellow to blue. Universal indicators, just a mixture of different indicators that gives you different colors for the different values of pH. You might have used pH paper, which contains that indicator, but you can also have it in its liquid form. There's many indicators, and we're going to use phenolphthalein primarily, but I want you to get that different indicators change different colors at different pH ranges. So you've used pH paper before, or you may have used it, where again you get multiple colors for the different pH values. Here there's a solution, and you have to figure out if it's NaOH or HCl based on the color that it changed. You can pause the video to try it yourself before I give you the answer. So here we can take a look that when we dipped it in the solution, it became green, which is a pH of 9. This one here became red, which is a pH of 1. So this is our acid, which is our HCl, and this is our base, which is our NaOH. So you have to make that connection between the concept of what's an acid, what's a base, and then the pH, how that connects to acid and bases. On this slide, you can see some more examples of indicators with a visual representation. So just to show you how that works over here, if you take a look over here, methyl orange, you can see that at pH 0, 1, 2, 3, and a little bit higher than 3, it's red. But once you start getting to that 3.2 to 4.4 area, it starts to turn yellow. So it goes from red to yellow there. But so what that means is if you have methyl orange and it's red, you know that it's probably less than 3.2 or 3.2 or less. If you have methyl red, for example, you'll notice that it's red from 0 all the way up to 4, 4.7, 4.8, you can see that in the table here, and about 4.8 to 6, it changes that yellow color. So if you have yellow methyl red that's yellow, that means that that solution is 6 or higher, and you know that much. So typically, because these indicators change colors at different ranges, when you use one, you have a general idea of where the pH might fall in, but you don't have a specific value. So sometimes you might need to use more than one indicator to figure out where your solution lies in terms of the pH. Even phenolphthalein, for example, we commonly say that it's acidic it's pink in basic solutions and then colorless in acidic solutions. But in reality, if you look at phenolphthalein, at 8.2, that's when it starts to turn pink. So for a little bit, just slightly above 7, it's still colorless. It really only starts to turn pink at that 8.2 range to 10 range, where it goes colorless to pink. So if you're pink, you know you're at your 8.2 or above in terms of your indicator. So you should be able to figure out roughly what pH you're at using the different indicators that we learned about. So you wouldn't have to memorize where all these indicators change color, but if I gave you an indicator scale and I gave you a color, you should be able to figure out roughly what pH your solution is at. So now we're going to talk about the pH scale in a bit more detail and do some calculations related to the pH scale. These are the main formulas that you're expected to know. So to calculate pH, you use the log button on your calculator. You do the negative log of the concentration of H+. To calculate pOH, which is a measure of the hydroxide ions, you do negative log of the concentration of OH-. If you want to go backwards, if you want to go from the H+ concentration, if you want to figure out H+ concentration from pH, you simply do 10 to the power of negative pH. If you want to figure out your OH- from your pOH, simply do 10 to the power of negative pOH. And you can actually convert from pH to pOH by knowing that pH is equal to by knowing that 14 is equal to pH plus pOH. So that means that if you want to calculate your pOH from your pH, you could simply do 14 minus pH. We'll do some sample problems on the next few slides. I've included some videos and some tutorials that you can go watch or attempt more practice problems on for the pOH and pH calculations. You can attempt those before trying the ones on this video. It's your choice. Just make sure that you do practice some. So here we have our definition of pH, pOH, and then some rules that we discussed. This is another rule. I'm not going to talk about this too much, but essentially if you multiply the concentration of the OH by the concentration of the H+ in a solution, you always get 1 times 10 to the power of 4. So when a solution becomes more acidic, the OH, more basic, the OH goes up and the H+ goes down. But when you multiply them together, you're always going to get this number here, 1 times 10 to the power of negative 14. And look at that, 14, that high value on the pH scale. And look at that over here, 14, the high value on the pH scale. So we're going to do some sample problems together. There's a little rule I want to go over first. If you have a strong acid and I give you its concentration, so let's say, for example, I give you the concentration of this strong acid over here, 0.010 mole per liter HNO3. The concentration of that strong acid will give you the concentration of the H+, because there's 100% ionization. So all of this acid is going to ionize to form H+ and NO3. So if I had a concentration of 0.010 molar over here, it's going to be the same over here. It's a 1-to-1 ratio as well. So this is not true for weak acids because they don't have 100% ionization. You can't assume that the concentration of your acid is going to be the same as the concentration of the H+. The concentration of the H+ is actually going to be a lot lower than the concentration of your acid because there's no 100% ionization, whereas here it is. Here all the acid is converted into H+. So you can take the concentration of the acid to be the concentration of the H+. Now, you'll notice I put the word monoprotic acid. HNO3 is a monoprotic acid, meaning it only has one proton to give away. Other acids are called diprotic, meaning they have 2 protons, or triprotic, 3 protons. So this H2SO4 will give away an H+ in solution. But it has another one to give away as well. But the problem is that this one here that it has to give away won't ionize 100%. So in reality, if you have H2SO4, it gives away more protons in solution. And there is a way of figuring out how many more protons it gives away, but it's not 2 times the amount for a diprotic acid. So I'm not going to give you too many of those to do. Most of the pH is actually dictated by that first dissociation here, but there's more to it than that, which you would learn in grade 12. So we're going to focus mostly on these monoprotic acids, where you just get a simple acid that gives away 1 H+, you figure out its concentration, and then that gives you the concentration of the H+. So that's my first step. If I want to find the pH of a 0.01 molar HNO3, I'd first find the concentration of H+, and then I would do the negative log of that concentration. So pH is equal to negative log of the concentration of H+, which is 0.01, and then that gives me a number. So you can try that in your calculator. Do the negative log of 0.01, and you should get 2. If you wanted to find the POH, you would simply do your 14 minus your pH, which is 2, and that would give you 12. Now, you can determine if a substance is an acid or a base using the POH scale, but since you're used to using the pH, go from the pH. Based on the pH, this solution is acidic. If you're given, so you can try that same problem over here, similar concept, just a different concentration. I would practice doing that ionization equation just to show that the concentrations of acid and H+ are the same. In this question here, you need to be very careful. The last question here, you're asked for the POH of a solution, and you're given the concentration of the acid. So you're going to find the concentration of H+ first, and when you do that, you're going to do your negative log, and you'll get your pH. And a lot of students would just stop there. Remember, we're asked for POH here. So think about that carefully. I'll write the answer out. Pause the video to try it yourself. Write all the steps. It'll write the answer out for you so you can see if you're on the right track. So our POH should be 11.4. Because your pH is negative log of 0.0025, which is 2.6. 14 minus that 2.6 is 11.39. I just rounded to 11.4. So try these problems out. Make sure you can calculate the pH and POH of an acid from its concentration. And now I'm going to show you the similar type of problem with bases. So for bases, it's the same general idea. The concentration of the base will tell you the concentration of the OH, with one additional rule. If you have a base with multiple hydroxides, providing it's a strong base, you can actually dissociate the entire thing and double its concentration. So here's what I mean by that. Let's do this sample problem here. NaOH dissociating to form your Na+. Remember, AQ should be written next to them, and OH minus. So if my concentration here is 0.0010 molar, then my concentration of hydroxide is 0.0010 molar. And if you wanted to find the POH, you'd simply do the negative log of your hydroxide concentration. And then if you wanted to, in the question asked, you could find the pH from there as well. But here we have 0.0010 molar. So you can do your log of 0.0010, and you get a pOH of 3. Now remember, you couldn't say that this solution is acidic because it has a pOH of 3. You have to look at the pH value. Its pH value would be 14 minus 3, which would give you 11. So in reality, this solution is basic. The pOH scale is the opposite, right? If you have a lower pOH, you're more basic. If you have a higher pOH, you're less basic. So just don't get confused by that. We weren't asking for that there, but I just want to touch upon that just in case you got confused. Now, I want to go over the other rule here. Here we have calcium hydroxide. We were given its concentration. It's a strong base, so it's going to dissociate. Remember I said for bases, they can dissociate 100%, and you can even take away all their hydroxides when you're doing that. It was different for acids. For acids, you just do one H plus at a time. But for bases, you can take away that entire hydroxide, so you have 2 OH minus here. That being said, this CaOH2 is going to be more basic. It's going to have more hydroxide ions if it's the same concentration, of course, as the NaOH. So our concentration over here is 0.0010 molar, but our hydroxide is going to be 0.0020 molar because of that 1 to 2 ratio. So to do your pOH, you'll do your negative log of that hydroxide concentration, the negative log of the 0.0020. So negative log of 0.0020, and you get 2.69. And that makes sense. It is more basic than the pOH of 3. A lower pOH means a higher, means you're more basic. If you want to convert that to pOH just to see that pH just to see that I'm telling the truth here, and we can compare pH values, you'll do minus 14 or 14 minus the pOH. You get 11.3, which is higher on the pH scale than the other solution in A. So it's more basic than the solution in A over here. So there's some more sample problems for you to attempt. Here you were given the concentration of the base, and in the previous slide you were given the concentration of the acid. Sometimes you might have to calculate the concentration of the base or acid before you actually can continue with the problem, and we'll do a few of those problems on the next slide. So you can try these ones here on your own. Actually, this one you should be able to do. You have your 2-liter solution of HCl with a concentration of 0.6 mole per liter. Find the H plus ion concentration, the pH, pOH, and OH minus ion concentration. So it's kind of organized so that you can actually do this sequentially. Sometimes some of the numbers in here are distractors. You don't really need to care too much about this 2 liters here. So, like I said, there will be some questions where you don't have the concentration right away. You have to figure out the concentration before you can figure out the pH. So over here, we want to find the pH of a solution that has 25 moles of nitric acid dissolved in 5,000 liters of water. So remember, nitric acid is HNO3. It's a strong acid, so it will dissociate, ionize 100% in water to form H plus and NO3 minus. And remember that the pH is always going to be the negative log of the concentration of H plus. Now we don't have the concentration of H plus, we don't have the concentration of anything at the moment, but we can find the concentration of the acid by simply doing the C is equal to N over V. And so that's going to be our 25 moles divided by our 5,000 liters. It's a lot of water. So 25 divided by 5,000, and you get 0.005 molar. Remember, the concentration of the acid is going to be equal to our concentration of the hydrogen ions. And now we can do our pH calculation. Negative log of that number, of our 0.005. And we get a pH of 2.3. It's the same idea for this question here. I'll let you try it yourself. But before you can actually calculate the concentration of the HCl, you need to figure out the moles of the HCl. So remember that, you need to figure out the moles of the HCl. So you can pause the video, try it yourself, and then you can take a look at the solution that I'm coming up with. So we ionize our HCl to form H plus and Cl minus. We have 0.009 grams of hydrochloric acid. So remember, we want to find the concentration. We have the volume, 0.1. Let me just erase that. We have 100 mils. We want to convert that into liters. So divided by 1,000, 0.1 liters. We need the number of moles. Remember, your moles can be your mass over your molar mass, which is 0.009 grams, divided by the molar mass of HCl, which is 1.01 plus 35.45, 36.46 grams per mole. Cross grams out, and you get 0.00024. I'm going to just round it there to 2.000247 moles. And then we can divide by our volume to get our concentration. So C is equal to N over V, so divided by 0.1, and we get 0.00247 moles per liter. That's going to be the concentration of the H plus. You have to write it down, and then you can do your negative log of that concentration to get the pH value. Negative log of concentration of H plus, and that should give us 2.6. And it is less acidic than the previous solution, which would make sense because our concentration over here was 0.005. Our concentration over here is 0.002 for the hydrogen ions. So it's a lower concentration of hydrogen ions, which means it is a little less acidic than our previous solution. So here's a few problems that you need to think about now that we've gone through the concept of acids, bases, strong bases, and concentration. So think about this very carefully. Two acids have the same concentration. One has a pH of 5 and the other has a pH of 2. How can this be? So they have the same concentration, the acids, but one has a higher pH and one has a lower pH. Think about that carefully. Same concentration of acids. Acid A, so we'll call it HA, has the same concentration as acid B. Yet acid A has a higher pH. It's somehow less acidic than acid B, which has a lower pH, 2. Think about the concepts we learned. Pause the video and reflect. That's right, if you said that acid A is probably a weak acid and didn't ionize 100%, then you're correct. That's what it was. Even though they have the same concentration, our acid A might have been a weak acid and acid B might have been a strong acid. So one factor that affects pH is, well, how strong or weak the acid is. Typically, if they're the same concentration, the strong acid will have the lower pH. Now here's an interesting question. A strong acid has a pH of 6.5. That's a high pH. You might be thinking, well, I thought only weak acids had a high pH. Not necessarily. Think about that carefully. How can that be? Pause the video and reflect. Okay. If you said that it's probably because the concentration of the acid was low, that's what it is. So HCl, for example, is a strong acid. But if you have a low concentration of HCl, you're going to have a low concentration of the H+. In fact, to have a pH of 6.5, your concentration of acid was 10 to the power of negative 6.5. Remember, to find the concentration of acid, you do 10 to the power of your concentration, your negative pH. So if you put that in your calculator, that's 0.001, 2, 3, 4. So 6 zeros, 3, 1, 6 molar. So you can have a strong acid in a solution. It's a very, very dilute solution where your pH is high. So don't always look at the pH of an indicator of whether something is a strong or weak acid. So if you do have the same concentration of acids and one happens to be higher and lower pH when you're comparing them, then you can use that idea of strong versus weak. But now if you only have one acid and you're given one pH, you can't necessarily justify your answer in saying this is a weak acid because of the high pH. It could be a very dilute solution. So the factors that affect pH are really, first of all, the strength of the acid and the concentration of the acid. So a strong acid, if it's a high concentration, it's going to be a low pH because there's an ionization, 100% ionization. But that strong acid could have a high pH if it's dilute. So it has a low pH if it's concentrated enough, but it could still have a high pH if it's very dilute. A weak acid, on the other hand, if it's dilute, it's going to have a high pH. It's going to have a high pH in many cases, but you can make a very, 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 very concentrated solution of weak acid and have a fairly low pH as long as you have a concentration of a very high concentration. So if I put enough weak acid into a solution, I'll have enough hydrogen ions to get me to a lower pH. So you have to think about strength, but also concentration of the acid. So clearly here we have our strong acid, and here we have our puny acid. So now we're going to take a look at a problem where you might have excess and limiting reagents. So I'm going to walk you through this, and then there's a few more problems that you can try on the next few slides yourself. This will require some stoichiometry. So we have 100 mils of 1.0 molar HCl reacting with 16.0 mils of 3 moles per liter NaOH. So let's write that out. So we have HCl reacting with some NaOH. And usually you would say this is a neutralization reaction, which it is. And if I asked you what is the pH going to be, you might say 7. But you need to make sure you look carefully at the amount that's reacting here, the molar ratios. So let's write everything in here. A volume over here is going to be 0.1000, there's 4 sig figs, liters. Our concentration over here is going to be 1.0 molar. So that means our number of moles over here is going to be C times V, 0.10 moles. So now we'll try the same thing over here. We have our base, which has a volume of 0.016 liters, and let's make it 60 liters, and our concentration is 3.0 molar, so our number of moles, C times V, 3 times 0.016 is 0.048 moles. I'm going to finish the reaction up just to get the right molar ratios here. So H2O liquid, and then our salt forms as well, plus NaCl. AQ. It's a 1-to-1 ratio everywhere. So let's take a look at our next question. So which reactant is in excess? Well, it's a 1-to-1 ratio. So if you had 0.10 moles of HCl, it should react with 0.10 moles of NaOH. That's what it should react with. But notice we don't have 0.10 moles of NaOH. We have 0.048 moles. We have less than 0.10 moles. So that means NaOH is our limiting reagent. The other way you could have looked at it was, we have 0.048 moles of NaOH. It should react with 0.048 moles of HCl. It will react with that. But we have more than that. We have 0.1. We have more than we need. So HCl is our excess reagent. So a neutralization reaction is going to happen. You're going to have 0.048 moles of NaOH react with 0.04 moles of HCl, but there'll be some leftover HCl. So in reality, on our product side, these are our products that formed, but there'll be, you don't see it, leftover HCl because our HCl is in excess. So when your teacher does that demonstration with a neutralization reaction of HCl and NaOH reacting, and you say drink that solution at the end because it's neutral, well, it's only really neutral if we actually reacted the HCl and the NaOH in stoichiometric amounts. If we had, let's say, the same concentration and maybe the same volume. But here we have different concentration, different volumes going on that gave us different number of moles, not reacting in stoichiometric amounts. So we have leftover acid. If your teacher drank that, your teacher would get hurt because you have some acid in there. And it's some dangerous acid in this case that should not be going down your esophagus, that maybe would be better in your stomach. For example, hydrochloric acid. I'm not saying drink hydrochloric acid, but you do have it in your stomach. So based on your answer in A, would you expect the final solution to be acidic or basic? So don't say it would be neutral because it's a neutralization reaction. Yes, it would be maybe less acidic than originally over here, but it would still be acidic in the end because there's excess acid. So it's acidic because there's excess acid. Now, we're going to mix the solutions together. We're putting HCl with NaOH, and we need to figure out what the final volume of the solutions are after mixing, and that's going to be important in a few minutes here. After mixing, our final volume is simply going to be our well, let's do it in mils first. It's going to be our 100 mils, 100.0 mils, plus our 16.0 mils. Right, because we mix the two solutions together, and it should be 116.0 milliliters. Now, the reason I calculated this is because we're going next into our question, which is what is the final concentration of the excess reactant? So to find that, we know C is equal to N over V. We have V now. We know V is 0.1160 liters. We need N. Don't go up here and say that N is 0.10. N is not 0.10. N is the leftovers we're looking for. 0.10 moles minus how much will react. So just like figuring out how much excesses are left over. So 0.10 moles minus how much would react or will react, 0.048 moles. And that gives you your leftover. So 0.1 minus 0.048. And we get 0.052 moles left over. So now what you can do is you can figure out your concentration by doing N over V. So C is going to be equal to our 0.052 divided by 0.1160, and we get 0.448, so I'll just say 45 molar HCl, because we have a new volume now. It's more dilute. It's in a larger volume. and also we have less moles. So now that leads into our last question, which is, what is the final pH of the solution? So remember, if you have the concentration of the acid, HCl, AQ, when we ionize it, it's 100% ionization. So that concentration of our acid will give us the concentration of the H+, which is 0.45. If it was a base and you had a 2-to-1 ratio or 1-to-2 ratio, you'd multiply that, but acids, we're just going to stick with our typical monoprotic acids. And now we can find our pH by doing the negative log of the H+. So and we have a very low pH there, 0.35 is our pH. So our solution is acidic. There's leftover acid. The rest of the solution was neutralized, but the HCl remained because it was excess, and that's why our pH is low with 0.35. So when you have problems like this, you need to make sure that you figure out which one's excess based on the molar ratio. If the acid is excess, then your solution will remain acidic at the end, less acidic than what it might have been to begin with, but still acidic nonetheless. If your base was excess, then your solution would have been basic, less basic than the NaOH was to begin with, but nonetheless still basic. If you want to find the final pH, you'd have to make sure you found the new volume because you mixed the two solutions together, so you have a new volume, and you'd have to make sure you find the leftover moles of whatever was left over. Then you'd have to calculate your actual concentration by doing your C is equal to N over V, so leftover N over nu V, right? So leftover, so let's call it LO, over nu V, V nu, or V mixed, or V additive sometimes we'll say. Additive means they add together. And then what will the final pH be? Well, then you do your concentration, your pH calculation based on the concentration you found in the previous question. All the other rules still apply for calculating concentration of H+ and OH-. It's just a few different steps to do when you have this type of stoichiometry question. And so there are some more practice problems for you to do on the worksheets provided in class, similar to the one that we just did in the previous slide. Here are some more practice problems for you to attempt. It's important that you try the readings and the problems in the readings as well to make sure that you know how to do these type of calculations.